Did you share your screen, by the way?
No, I don't think so. Hold on. I just do that.
You can do command.
All right. I'm sure.
Yeah. Meanwhile, welcome everyone to the last lecture of Seminar in Computer Architecture, TTH Zurich. For today, we will have 3 sessions, so we may take more than for around 3 hours. So, Konstantinos, whenever you are ready, feel free to introduce Maria.
Mohammed, can you see the share screen?
Yes, we can see the slide, but not your face.
Yes, turn on the camera.
Yeah, please.
Now? Yes, you can probably.
Yes, I think it's perfect. And you are live.
So the first presenter is Maria Makenkova. She's a 4th semester student at the Computer Science Department, and she has a strong interest in computer architecture, DRAM, and true random number generators. Good luck, Maria, and looking forward to your presentation.
Yeah, thank you for the lovely introduction. As you just mentioned, I'm going to be talking about the QUAC-TRNG paper, which introduces a true random number generator that induces entropy in commodity DRAM chips using a process known as quadruple activation. Now, before we dive into that, I'd like to give you a quick executive summary of what is to come. If I can. Here we go. As many of you might know, true random numbers are quite present and used across many different workloads in different computing systems. However, generating true random numbers requires specialized hardware, which not all computers have. This limits the ability of some computing systems to run workloads that require true random numbers. This is exactly the problem that the paper tries to tackle by providing the design for a true random number generator that uses commodity DRAM chips as an entropy source to generate random numbers. The key idea behind that is to use something called quadruple activation to induce metastability in the DRAM sense amplifiers, and this is then used as an entropy source. Now, before we continue, let me quickly give you some background on true random number generation. As I mentioned before, there are many use cases for random numbers, like cryptography, like signature generation, or in scientific simulations, especially in Monte Carlo methods, or in machine learning, for example, for randomized training. A true random number or a random number generator is a device or a program that generates random numbers. And here I'd like to distinguish between 2 kinds of random number generators: pseudo-random number generators and true random number generators. These are mainly different in the way of how they produce random numbers. A pseudo-random number generator would take an input value called the seed and then perform arithmetic transformations on that seed until it appears random. While a true random number generator would sample a random physical process, an entropy source, to generate the random numbers. There's also another fundamental difference between the two, namely the fact that if the seed is compromised, a pseudo-random number can be easily regenerated by performing the same arithmetic operations on the seed. Now, however, for the true random number, this is not possible since you can't generate the same sequence by observing the same physical process again. This makes true random numbers fundamentally more secure than pseudo-random numbers. However, there is a tiny flaw to true random numbers, mainly that they are often biased, meaning that the output of the sampler, the device that would sample the entropy source, often contains more ones or more zeros. This could be due to the entropy source itself or the device used to sample that source. In either case, post-processing is needed to remove the bias and improve the quality of the true random number. I'm going to really quickly introduce two methods of post-processing that are relevant in this paper. Firstly, cryptographic hash functions. These perform arithmetic operations on, bless you, an input bit stream and to scramble and randomize it. Secondly, the von Neumann corrector. This takes the output of the sampler, like the bit stream, and groups it into groups of 2 bits each. Then depending on what these 2 bits in the groups are, the following operations are performed. If both bits in a group have the same value, the entire group is removed. If the 2 bits are 0, 1, then they are replaced by a 1, and otherwise they are replaced by a 0. So for example, if you consider sequence 0, 0, 1, 0, the first 2 bits are the same, so they would be removed. And the latter 2 bits would be replaced by a 0. So the sequence after the von Neumann corrector would become 0. Now let's quickly cover some challenges that we currently face in generating true random numbers. As I mentioned before, true random number generators require specialized hardware, like chaos circuits, for example, and not all computing systems are equipped with such. This limits the capacity of many computing systems to produce true random numbers and to use them in applications that are run on these systems. The goal of this paper particularly is to design a true random number generator that uses DRAM to generate random numbers with high throughput and low latency. Now, in DRAM, true random number generation has many advantages. Firstly, as a lot of you might have noticed by now, DRAM is pretty omnipresent and a lot of computing systems use it. Secondly, as described in the paper, QUAC-TRNG, the true random number generator, can be implemented at relatively low area cost and hardware cost too, which kind of correlates. Anyways, also that would enable in-memory true random number generation, which would lead to less data movement. It is also optimal for processing in-memory workloads, and it would avoid communication with designated true random number generating hardware. Additionally, true random numbers at high throughput would be great since they would allow more applications to use true random numbers on commodity machines. Now, before we go on to actually exploring how true random numbers are generated in DRAM, let's have a look at some DRAM background. Since we have seen quite a bit of this in previous presentations, I'm going to go relatively quickly through this, but do feel free to interrupt if anything is not clear. So in a typical system, the CPU's memory controller communicates with a set of DRAM chips over a memory channel. A single DRAM chip is made up of multiple DRAM banks, which are all connected to the same chip I/O. A DRAM bank, in turn, is organized into DRAM subarrays, which contain word line drivers and sense amplifiers. The subarrays themselves are partitioned into DRAM mats that are separated by word line drivers. And a DRAM mat is basically a collection of DRAM cells. And here you can see that a row of DRAM cells is also known as a DRAM row. A DRAM cell itself can be simplified in the following diagram. And now let's have a look at how we would access the data stored in such a DRAM cell. The data in a cell is stored as charge on the capacitor, which is connected over an access transistor to the word line and the bit line. And over the bit line, it is also connected to the sense amplifier. The bitline bar value is used in the process of sense amplification, and it is basically the inverse of the bitline value. The sense amplifier has an enable signal, which turns it on or off. Initially, the bitline voltage is precharged to half VDD. We can also see that in this example, the capacitor is fully charged. This is indicated by the gray coloring. This means that this particular DRAM cell stores logic 1, Now, in order to read the data stored in a cell, first we need to enable the word line. This connects the capacitor to the bit line over the access transistor, since this one is now activated. Since the capacitor is charged, it has a higher charge level than the bit line, which is at half VDD. So the capacitor the charge would flow from the capacitor to the bit line. This leads to the fact that the bit line voltage is deviated slightly towards VDD. Now, at this point, the sense amplifier is enabled. It compares the bitline value to the bitline bar value. And in this particular example, it amplifies the bitline voltage towards VDD. Now, as you can see, the capacitor is still connected to the bitline. So the simplification process also restores charge in the capacitor. Now let's consider how this would look for an entire DRAM subarray, which you can see schematically here. These are two DRAM rows. Let's say the top one is row 0 and the bottom one is row 1. Both are connected to word line drivers and sense amplifiers. DRAM cells are usually accessed in cache line granularity. If we want to get the data that is stored, for example, in row 0, we need to perform the following sequence of DRAM commands. First, we would issue an activate command to row 0. This has the effect that the data stored in this row is copied to the sense amplifiers. Afterwards, we can read the data from the sense amplifiers by issuing read commands in cache line granularity, and data is usually read in cache line granularity. Now, if we want to read the data from the other row, row 1, we would first need to close row 0 by issuing a precharge command. This restores the bitline voltage back to half VDD. Afterwards, we can issue an activate command to row 1, and once again, copy the data to the sense amplifiers and read it in cache line granularity. Now, in order for all of this to work properly, the memory controller needs to obey specific timing parameters when issuing commands to DRAM. I'm quickly going to cover two timing parameters that are specifically relevant to QUAC. Firstly, activate and precharge commands must be interleaved by TRAS. This is basically the time that a cell needs to restore its charge. Precharge and activate commands must be interleaved by TRP. This is the time it takes to settle the bitline voltage back to half VDD and disable the activated word line. This concludes the background knowledge, and now we can dive right into exploring TRNG. So the main idea behind QUAC-TRNG is to issue a series of activate, precharged, activate commands that you have seen before to DRAM while significantly violating timing parameters. This you can see in this graph. At the bottom in gray are the timing parameters that you are quote unquote supposed to use. And on the top are the timing parameters with which these commands are actually issued. The result of issuing those commands is that 4 consecutive rows in DRAM are active at the same time, since they are turned on in really quick succession. This is something the paper refers to as quadruple activation, or QUAC. And the paper also shows that this behavior can be induced reliably in DRAM chips by the manufacturer SK Hynix. Now, in order to understand how this works, we need to first quickly have a look at DRAM organization, more specifically hierarchical DRAM organization. This organization consists of hierarchical word lines. You can see a master word line and a local word line. So in order to read a row in DRAM, one would take the following 2 steps. First, we select the correct master word line, and note how there are 4 local word lines all connected to the same master word line. After we've selected the right master word line, we would use one of the control signals to select the proper local word line or DRAM row that we actually want to read. Now, in order to see how this can be used in order to activate 4 DRAM rows at the same time, let's consider a hypothetical row decoder as shown in this diagram. This hypothetical row decoder operates on the 2 least significant bits of the address and uses those to drive latches, which drive control signals, and the control signals S0, S1, S2, and S3 drive the corresponding DRAM rows. So in the first step of QUAC, or quadruple activation, we would issue an activate command to row 0. You can see that also already highlighted on this diagram in red. This drives the latches A0 bar and A1 bar, and added together, those drive the control signal S0, which activates row 0. In the second step, we would issue a pre-charge command. But since the timing parameters are violated, the pre-charge command does not have enough time to deactivate the latches that were already driven by the first activate command. So when we issue the next command, another activate command, this time to row 3, those latches are still active. But the activate command to row 3 also activates the latches A0 and A1. So now that all of the latches are active, this drives all 4 control signals for all 4 rows. And as a result, all 4 consecutive DRAM rows are active at the same time. Now let's have a look at how this behavior can be used to generate random numbers. In this schematic, you see 4 DRAM cells along the same bit line. Note that the charge level in the DRAM cells alternates. So the black ones are logic 1, and the white ones are logic 0. Logic 1 is charged, 0 is uncharged. Initially, the bitline voltage is pre-charged to half VDD. Also here in this figure on the right, you can see the difference between the 2 ends of the bitline, which is sampled by the sense amplifier. At the beginning, this is 0, because both bitline and bitline bar are at half VDD. Also, in the dotted lines, you can see the reliable sensing threshold. So in order for the sense amplifier to correctly sample the bitline voltage needs to be outside of the 2 lines, so either below or above. Now, when we issue the first activate command to row 0, this connects the cell in row 0 to the bit line, and the cell begins to share its charge with the bit line. This has the effect that the bit line voltage deviates slightly towards VDD. Then we issue a pre-charge command, which is quickly interrupted by another activate command, this time to row 3. As we have seen with the hypothetical row decoder, this now activates the remaining 4 rows, and all 4 rows contribute to the charge of the bit line. As you can also see in the graph, the difference between the ends of the bit line is now below the reliable sensing threshold. So when the sense amplifier is turned on, it cannot reliably sample this bitline voltage. So what it does, it settles to a random value, 1 or 0, based on any random factor like thermal noise. And with this, we get a random value in the DRAM sense amplifier. Now let's have a look at the QUAC-TRNG mechanism as a whole. This can be summarized in 4 steps. Firstly, the segment initialization step. So we have 4 rows on which the QUAC operations are performed. Those need to be initialized with a conflicting data pattern. This is done using in-DRAM copy operations. So you would have 2 rows, one storing all 0s and one storing all 1s, and you would copy the data from those rows to initialize the QUAC rows. Next, QUAC is actually performed on the 4 QUAC rows. And the third step, the data is read from the sense amplifiers and grouped into 252-bit entropy blocks. These blocks are brought to the memory controller for post-processing in step 4. And for post-processing, the SHA-256 cryptographic hash function is used. The result of the whole procedure is a 256-bit random number. Now let's have a look at the experiments that the authors of the paper have performed with QUAC, the results that they have achieved, and the conclusions they have drawn from those results. First, this is the testing setup. In total, 136 DRAM chips from 17 off-the-shelf DDR4 modules by the manufacturer SK Hynix were tested. The authors have used a modified version of softMC to issue DDR4 commands directly to the DRAM from an FPGA board. The experiment was also temperature controlled at 50 degrees Celsius. In order to quantify the randomness of a bit stream that was generated using QUAC, the paper proposes we use Shannon Entropy. Shannon Entropy basically measures the signal present in any bit stream. It is calculated according to the following formula, where P is the probability, which basically translates to the proportion of logic 1 and logic 0 values in a bit stream. If you want to think about it intuitively, if you have a stream of only ones, then the Shannon entropy of this would be 0. And if you have a stream where you have a roughly equal amount of ones and zeros, then the Shannon entropy would be close to 1. In order to gather the bit streams to test for Shannon entropy, QUAC is performed 1,000 times, and for each sense amplifier, we thus get a 1,000-bit bit stream. The first thing that the paper analyzes is data pattern dependency. So here it assesses whether or not the data pattern with which the 4 rows are initialized contributes to the amount of entropy that QUAC produces on those 4 rows. For this, at 50 degrees Celsius, 8,000 DRAM segments are initialized with 16 different data patterns across 17 different DRAM modules. For example, for data pattern 111, we would have the following. All of the rows are initialized with just ones. For data pattern 1000, on the other hand, you would have row 0 initialized with ones and the other 3 rows initialized with all zeros. In order to quantify the results, the paper proposes cache block entropy. This is the sum of all the bitline Shannon entropies in a cache block. So basically, we have bitlines and each of them has a sense amplifier, and we can collect a bit stream from that sense amplifier, and then the sum of all the entropies is the cache block entropy. The maximum value for which is 512, since this is how many bitlines you would have in a DRAM cache block. We also have average cache block entropy, which is the average across all cache blocks in a module, and the greatest cache block entropy, which is the greatest maximum cache block entropy in a DRAM module. The results can be summarized in the following graph. The x-axis shows the different data pattern used. Now, it's a bit fewer than 16 because this graph only plots the data patterns that actually produced a significant result. And the y-axis are the average entropies. Here in gray, you can see the average cache block entropy, and in orange, you can see the maximum cache block entropy. Also note that there are different scalings on either side of the graph for those. The error bars represent maximum and minimal values across all DRAM modules. As you can see, the entropy greatly varies depending on which data pattern we use for initialization. And the most entropy is achieved with data pattern 0, 1, 1, 1. The authors hypothesized that this is due to the fact that row 0 is initialized with the opposite value to the other 3 rows. And since row 0 has the longest time to share its charge with the bit line, this would produce the most random results. Another thing that was experimentally analyzed is the spatial distribution of entropy. Basically, how does the entropy vary depending on the physical location of a DRAM segment on the chip? For this, segment entropy is defined. This is very similar to cache block entropy, except here we sum the bitline entropies in a DRAM segment. So here, the maximum value is larger. That will be 64,000 because this is how many bitlines you have in a DRAM segment. The data pattern used for initialization in this experiment is 0111, which was previously found to be the most random in the experiment you've just seen. Here you can see the results. The x-axis plots the 8,000 DRAM segments in a DRAM bank across 336 DRAM chips, and the y-axis shows the segment entropy. The red curve shows the average segment entropy across all chips, with the error bars showing the maximum and minimum entropy values observed for any DRAM segment. The dotted curves depict 2 modules like the blue and the black. that's the word, black curve depicts two modules that provide representative samples of two major entropy deviation trends. We can see generally all curves exhibit sort of a waveline pattern. The paper authors mainly attribute to systematic process variations. Other theories they have that might explain this deviation would be post-manufacturing row repairs, where after the chip is produced, the rows are remapped because there are faulty cells or things like that. So you would have two rows that are logically adjacent, but not actually physically adjacent on the memory chip. Another thing could be the segment's distance from the sense amplifier. You can also see that the curve kind of peaks at the end and then drops. And this, the authors of the paper explain mainly with differently sized DRAM subarrays at the end of a DRAM bank. The paper also runs a lot of experiments to try and determine the quality of the random numbers produced by QUAC-TRNG. And this is the experiment that they want to measure thus. So first, the highest entropy DRAM segment that was found in the previous experiment is initialized with the highest entropy data pattern. Then QUAC operations are performed on 4 rows in that segment. Then the data is read out from the sense amplifiers and split into 256-bit blocks. Those blocks are then post-processed with the von Neuman Corrector and the SHA-256 cryptographic hash function. Now here it's important to note that it's not both at the same time. It's either the von Neuman Corrector or the SHA-256 function. Then the results of that are fed into the NIST Statistical test suite. This basically measures the quality of a true random number generator. It runs multiple statistical tests on the bit sequence, which is the input, to try and figure out if it has any statistical properties. An input sequence can either pass or fail such a test. In this graph, you can see the results. The first column are the different tests that were run. The second test is the output post-processed with the von Neumann corrector, and the last column is post-processed with SHA-2. So in order for a bit sequence to pass a test, the p-value needs to be greater than 0.001. And as you can see, all of the bit sequences successfully pass all tests. This can be seen as an indicator of the fact that QUAC-TRNG produces high-quality random numbers. Now let's quickly have a look at the throughput of QUAC-TRNG. And the throughput for a DRAM module can be computed with the following formula, where SIB is a SHA input block with 256 bits of entropy. This value is then multiplied by 256, since a single QUAC operation produces 256-bit random number. L is the latency of a QUAC-TRNG operation, including the initialization of the 4 QUAC rows in nanoseconds. The results can be summarized in this graph. Here you can see the average, maximum, and minimum throughput in gigabits per second. It was also tested across 3 different configurations. Firstly, one bank, where only one DRAM bank was used to perform QUAC on. Secondly, BGP, which stands for bank group parallelism. Here, 4 different banks were used, and the DRAM commands were issued in parallels to basically explore bank group parallelism. Then the last configuration is BGP plus RC, where in addition to BGP, we also use row clone to initialize the rows within DRAM copy that further improves the initialization times. As you can see, the last configuration is by far most successful, and also the configuration that the authors of the paper recommend. You can also see that the average throughput of QUAC-TRNG is 3.44 gigabits per second. Now let's quickly have a look at system performance. System performance was analyzed with the SPEC 2006 benchmark suite. A 3.4 gigahertz core was simulated, and 4 DRAM channels were also simulated. Also, this relies on a perfect memory scheduler, which would only issue QUAC-TRNG commands during DRAM idle periods. Here you can see the results. At the bottom, the x-axis are the different tests within SPEC 2006, with the average in the end highlighted in red. And well, the y-axis is the throughput, once again in gigabits per second. So you can see the average throughput would be 10.2 gigabits per second, with a 3 gigabits per second and minimum and a 14 gigabits per second maximum. This roughly corresponds to 74% of the empirical average that I presented in the previous slide. Now, I'm not going to go into too much detail on this. The paper does, so if you're curious, do check that out. It is quite well explained how they performed all the different comparison tests. But I just wanted to show you this slide. This is the comparison to other DRAM-based true random number generators. And you can see QUAC at the top has the best true random number throughput, in some cases by far. You can also notice that it has a very high latency, actually the highest latency amongst its so-called competitors. To this end, the paper proposes to have a true random number buffer. So you would generate the random numbers and store them in the buffer. And then when an application asks for random numbers, you would serve it from the random number buffer. Now let's have a look at system integration. The SHA-256 function can be implemented at relatively low area and latency costs. This makes it really well suitable for implementation in the memory controller, and it only takes up 0.001 square millimeters of area. QUAC-TRNG itself has a memory overhead of 192 kilobytes. This corresponds to roughly 0.002% of an 8 gigabyte DDR4 chip. It also has an area overhead of 0.0003 square millimeters. So in total, with the SHA cryptographic function, one would only need 0.0014 square millimeters, which corresponds to a 0.04% of chip area to implement QUAC-TRNG in hardware. Now, before we move on to my opinions on the paper, let's just quickly cover the executive summary one more time. So we have seen that true random numbers are used across a wide range of different workloads. It is quite problematic that true random numbers require specialized hardware, which not all computers have, thus limiting their ability to run true random number intense applications. The goal of this paper was to address this problem by providing a high throughput and low latency true random number generator that works in commodity DRAM chips. The key idea behind which is to use quadruple row activation to generate metastability in the sense amplifiers and to use those as an entropy source. Now we have reached a point where I talk about the strengths and weaknesses of the paper. Overall, it was a fun and definitely very informative read. The paper explores a very new, interesting, and innovative idea, which also provides significant improvement, as you might have seen in the past few slides, especially in the area of throughput. Many aspects of the implementation are well analyzed, and all the experimental results are presented in a good way. And the authors also try to explain different behaviors that were observed by performing QUAC. And I feel like at this point, it's kind of important to know that since all the DRAM designs are proprietary, there's not really a way to know why a DRAM chip would act in specific ways and why you would observe certain specific phenomena. So I feel like the paper really does a good job in providing hypotheses to why certain things were observed. The paper also provides a lot of background on true random numbers and on DRAM itself, which makes understanding the concepts a lot easier. The concepts is also thoroughly researched, and results are presented in a really comprehensive way with a lot of graphs and diagrams that really eases the understanding and overview of the results. Another thing that I think is definitely a strength is the fact that this paper explores a processing in memory solution. And as we have seen in the scores, processing in memory is quite the hot topic nowadays in computer architecture. So it is nice to see a paper that also contributes to that a bit. Now, of course, no paper is perfect. So here are the weaknesses that I have personally found with this paper. Firstly, it has not really explored how QUAC-TRNG would interact on a system where processes are already running. They did run the system specifications, but it's not like they rely on a hypothetical scheduler that only schedules DRAM commands when the memory channel is idle. So it would we would not be sure how that would work if there would be enough time within those idle periods for the QUAC commands to complete. Also, it is not sure how much overhead this was produced, because you need to issue commands with reduced timing parameters. So this would definitely be different from the normal operation of DRAM. Another thing is that the paper was only capable of inducing QUAC behavior in DRAM chips by one manufacturer, namely SK Hynix. As briefly mentioned that 2 other manufacturers were tried, but those did not produce any results, so they did not exhibit any QUAC behavior. The last point is kind of a personal preference, but I found the writing style somewhat repetitive. Now, before we go into the discussion, I'd like to quickly circle back to the first point, because later another paper by roughly the same research group came out, which addresses exactly that. Namely, that is Dr. Strange, which is an end-to-end system design for DRAM-based true random number generators, which is kind of cool. So basically there, they provide the system design that consists of the following components. Firstly, a random number buffering mechanism. As you have seen, the throughput of QUAC-TRNG is pretty high, so you would alleviate that by having a random buffer which stores the random numbers. Then they use a DRAM idleness predictor to predict idle cycles and to generate random numbers during those cycles. This also reduces the interference in the system. Then they have a random number aware scheduler. This also reduces interference. Basically, you would separate random number generating requests to memory from not random number generating requests to memory and have them in separate request queues. And then based on priority levels of the programs running on the system, you would schedule either queue. Also, the paper provides an application interface that basically allows processes running on the system to request random numbers from DRAM. All right, overall, both papers I would highly recommend, especially if you're interested in that sort of thing. Together, they provide a really great insight into true random number generation in DRAM. Now we have already reached the point for audience questions. Now I think I'm going to quickly introduce the discussion topics so that you have time to think about them and potentially ask questions on the discussion topics. So I'm just going to quickly do that before I let you ask. So the first discussion points, are there potential dangers in violating DRAM timing parameters? Like, they must be there for a reason. Could we potentially induce RowHammer by using the same 4 rows over and over again to generate random numbers, especially with the violated timing parameters? Could this potentially reduce the quality of sense amplifiers, like accelerate the aging of the hardware itself? Could that affect data stored nearby? And of course, the most important question, how can we potentially solve these issues if they prove to be issues at all? Discussion point 2, it's kind of a weakness, but I personally don't think it's a weakness. That's why it's a discussion point. So currently there are not many specific workloads that would require such a high throughput of true random numbers. Like quantum key distribution is one of them, and also some very intense simulations would need that, but not many things you would use on commodity hardware. So is that future-oriented thinking, or is the paper trying to solve a problem that's not really even a problem yet? Can this potentially lead to future developments where more true random number intense workloads are available on commodity machines? Would that also in turn lead to improved security on such devices? Curious to see what you have to say about that one. And the last discussion point kind of ties into the previous one. Like, how do you see QUAC-TRNG implemented, and especially where and what kind of computing systems, what kind of workloads, present or imaginary future workloads do you see working on that, and what kind of computing systems? All right, before we dive into the questions, I'll just quickly like to thank my mentors for providing really, really helpful feedback and helping me to slide. And a lot of the slides you have seen, especially the ones with the pretty animations, they have gladly let me borrow from their presentations. So thank you so much. And I guess we can open up the round for questions. Do we need a microphone for the room?
what I wanted to ask you if the article describes what could be the effect of allowing thermal oscillation. So not keeping the temperature constant, but letting it vary, because I can hypothesize two scenarios. In one scenario, maybe this is another source of entropy that is not controlled, but on the other end, it could also be that under specific circumstances, we get more foreseeable results. So,
well, I'm glad you asked, because I actually have a backup slide on that. Wait, one back. Here we go, because the paper actually also studied temperature dependence, and I had to unfortunately cut this slide because I did not have enough time. So basically, they tested the highest entropy DRAM segment at different temperatures, 50 degrees Celsius, 65 degrees Celsius, and 85 degrees Celsius. And as you said, they observed two major different trends. In some chips, the entropy increased, and in others, it decreased. So basically, it definitely has an effect on the entropy, but it depends on the chip what that effect is.
okay, thanks.
Yeah.
Thank you. So what I was curious about is that the 100, no, the 0111 pattern seems to work quite nicely, but the I got it wrong. The 0111 pattern works nicely, but then the 1000 pattern didn't even produce a significant result.
You mean 1000? That would still be the second highest average.
Okay, so I
cache
just
block
missed that.
entropy. Yeah.
Okay.
I mean, it's significantly lower. Yeah, you're right. But I believe that is also dependent on systematic process variations.
Okay, and then in the same way, why are 4 values used? Could you also try it with 8 or just with 2? Do they talk about that in the paper?
You could try. It doesn't work with 2 because there's actually another paper that the authors list as an inspiration for this paper that manages to induce a different kind of behavior in DRAM by activating 2 rows at the same time. I don't know if it would work with 8. So I'm probably the wrong person to ask. So.
Okay, but it's not like a memory hardware constraint that you have to use for that operation.
I don't think so.
Okay.
Theoretically, probably use more rows, right? I mean, in theory. Yeah.
Okay.
But you know, since you've seen that the hypothetical row decoder, it's kind of important to be able to activate them all at the same time. And that only works with the issuing the commands if they are structured in the way as we have seen, and that works mainly only with 4 rows. I mean, fewer would probably theoretically also work.
Okay, and then if I may, a third question. In the beginning, when explaining the true random number generation, you mentioned post-processing of the bit stream.
Yeah.
Is that also done in this paper? With the generated bit stream, does it need to be post-processed?
Yeah, this is what is done with the von Neumann corrector and the SHA-256 cryptographic function. Hold on, let me find it. Yeah, here. Well, first of all, here, they use post-processing because the outputs of the sense amplifiers are indeed biased.
Okay.
Yeah.
So the bias is not alleviated with this method?
No.
Okay, thanks.
Yeah, so actually this is related to the post-processing. So with the SHA-256, aren't you really, when they perform the statistical test, are they really testing the SHA-256 for its statistical properties? Because even if you feed like a completely sequential sequence to SHA-256, then you will get random looking outputs.
Yeah, I was waiting for someone to ask that. So basically, hold on, almost there. Any second now. Here we go. So basically, they run the test with both the von Neumann corrector and the SHA-256. And as you have seen, the von Neumann corrector is a lot less invasive. And you see that also the sequences that were only post-processed with the von Neumann corrector pass the NIST statistical test suite. And this is kind of like a control group, so to speak, to say that we're not just testing the SHA-256 function, but also the actual output of the bit stream.
Yeah, I mean, like the von Neumann, though I understand it, it only triggers on any change, right? Because anytime you have like constant bits, you basically delete them. Mm-hmm. So I guess, yes, even the values for the von Neumann corrector suggest that it's more or less random. But yeah, you can see that there is quite a big dip. Just wanted to point that out.
Yeah, definitely. Thanks.
Any other?
Thanks. I was just wondering, did they explore in the paper why this sort of technique only worked on the SK Hynix DRAM chips?
Well,
like you mentioned that they said it didn't work on the other ones, but did you know why?
Well, there's not really a real way to know why, because you don't know how the DRAM chips are organized. But I talked with Atterberg about that, and he basically said that a lot of it has to do with the DRAM circuitry and how the, like when you issue a command, which rows are activated and how with the row decoder, that's the word. It has a lot to do with the row decoder. As we have seen with the hypothetical row decoder, in order to have, hold on. Almost there. Yeah. So basically, in order to activate 4 rows at the same time, you need to have this hierarchical DRAM structure. So this is definitely quite important. So it's probably the row decoder that is different, or maybe there is some kind of filter that doesn't allow you to issue DRAM commands with constrained timing to the DRAM. That could also stop it from inducing QUAC. So in a way, there's no way to know why it exactly didn't work, but those would be the 2 main hypotheses.
Okay, so they don't actually have an idea whether or not it's because they can't activate the 4 rows at the same time, or if it's the timing thing you said.
Well, they know they can't activate the 4 rows at the same time.
Okay.
That is the big issue. And that could either be because of the DRAM controller, or because there's some additional circuitry maybe that doesn't allow the violated timing parameters. That could also be a reason to why you wouldn't be able to activate 4 rows.
Okay, thanks. Anyone else?
Oh, well, in that case, thanks for your attention. Oh, no, actually, no, hold on. We have discussion questions. I'm not letting you off that easy. Does anyone want to contribute their opinions to the discussion questions? Yes, gladly. Sorry, this has too many animations. Gives you more time to consider which one you most like to answer. Nope. There we go. Discussion question 1. Maybe we could just do them in order, or if you have a preference, feel free. Yes, you need the microphone.
I believe this is, I think, your second discussion point.
Yes.
The one, or basically the idea that the paper is trying to solve like a problem that's that is not really a problem, because these days I think most computers already contain hardware that can produce pseudo-random numbers. I think now Windows even requires a TPM, which means that you have basically a high quality random source in most modern computers. So I kind of agree with this point that it is maybe a redundant task. But what I can kind of see is that if you do require like very, very high quantities of random numbers for like some statistical experiments, like we're talking about gigabytes of data, then I think this could be quite interesting, because you could fill up the entire RAM chip with random data very quickly. Well, you mentioned at the end very quickly the Dr. Strange paper, where they actually performed some did I understand correctly that they actually perform some kind of like where they can a real implementation where they try to run it on real hardware?
Let me quickly check. Is anyone presenting that paper after me? Because I don't want to take stuff away from them. No, good. Yeah, no. Basically, they haven't implemented it on real hardware, but they provide a lot of system that would enable to actually use such TRNGs on real hardware without like interruptions.
Mm-hmm.
I mean, of course, you probably need some more system integration, like maybe a specific like new command that would have the violating timing parameters in it. But that is more of like an ISA thing than a hardware thing, and both papers focus more on the hardware thing.
Yeah, no, it's very interesting approach, but I think it's kind of redundant.
Yeah, but now I'm thinking about what you said in the beginning, that the advantage of the true random number generator over the pseudo random number generator is that it's different in every system, right? Because it's true random numbers. So I think this is a real benefit if you would have actual true random numbers in every system by using the commodity DRAM, right? Because if you have some sort of way to compromise the pseudo random number generator that is in every system, then you have power over many computers at the same time, because they're the same, right? They react the same to the same input.
You would have also true random number generators in many computers. They would use like chaos circuits, for example, that are also TRNGs.
Right.
Okay. Although many systems use pseudo random number generators like dev.random if you run Linux. Yeah.
I mean, usually what you do is you have some kind of like slow true random number generator with which you seed a pseudo random number generator. I think that's like what the implementation is in most chips, like the TPMs, for example, that I mentioned. But yeah, they're basically, it's very difficult to kind of compromise them.
Definitely both good points. I agree with you to some extent, but I also think it's important to notice, similar to what you said, QUAC-TRNG kind of scales infinitely almost with DRAM bandwidth. And also it's a processing and memory solution. So if we were to go towards a more memory-centric architecture, it would definitely be something to consider.
If nobody has anything else, I just wanted to like add that something that just came up though, in terms of like compromising, like thinking about attacks such as RowHammer and so on. Wouldn't this sort of kind of expose the random number generator to a potential attacker, especially if we're talking about a system where you mentioned that the paper hasn't really talked about running this concurrently with other tasks, but say, for example, you are running it on a system which is also running other processes. I kind of see this as a big vulnerability where you could potentially kind of read out some of the random states from the RAM and thus compromise your random number generator. This isn't, for example, a case in terms of like really dedicated on-chip hardware, which is isolated.
Yeah, no, I can definitely see that being an issue, or stuff where you can like affect the temperature of your DRAM and thus like reduce the throughput of the generator. That could also be a potential attack, which could potentially be fixed because the paper talks about really briefly about like calibrating the chips and like knowing exactly where the highest entropy segments are for the different temperatures. And then depending on the temperature in your chip, choosing the right segment. But yeah, basically there are a few dangers in security that one could think of. Yeah. All right, I guess since there's 3 presentations today, we'll conclude it here. Thank you so much for listening and your contributions, and enjoy the other 2 presenters today. Thanks.
Yeah, I think while you're switching, maybe I'll make some comments. Can you hear me in the room? Hello?
Yes, Onur, very well.
Okay, great. I'll make some comments. Maybe if you stop sharing, people can see me in the room also. I wish I could be there, but I couldn't, yeah. Yeah, it was a nice talk. Thanks for the nice summary. And I wish we had more time for discussion also. Yeah. Basically, I think there were some discussion points, and I think security of random numbers is certainly important, and there needs to be good ways of handling security for sure. The other issue that was discussed is whether this is really redundant with existing random number generators. I think that's a red herring in my opinion, meaning that assumes that there should not, let's say, different ways of doing things are not necessarily useful. I think in research, it's really important to explore different ways of doing things, even though that way may not be, let's say, acceptable immediately. It may be acceptable 10 years down the road, or I mean, maybe 20 years down the road, right? So I think these works that produce random numbers inside DRAM, in that sense, are quite forward-looking because they're exploiting some fundamental phenomena that lead to random numbers. A complete different way of generating random numbers, true random numbers, than we have seen before. And yes, maybe existing processors implement random number generators that take advantage of process variations in different ways in the circuitry, but future processors may be much more data-centric, and you may want to have random number generators on the memory side, for example, and DRAM side. And maybe not every processor would like to have random number generators if they're low cost, for example. So it's good to think about it from that perspective. Yeah, maybe there are other complete different ways of generating random numbers. Okay, I think I will stop here because there's another talk, but I don't see anything being shared. I just see Konstantinos's screen. Are you ready over there?
Yes, can you hear me?
Okay, yeah, I can hear you, but I don't see the screen, so feel free to go ahead.
Where is the other microphone?
I believe you don't prefer to have your talk live streamed, right?
Yes, that's correct.
Okay, let me stop the live streaming then. I think the same for the next talk as well, so we won't have live streaming for people on YouTube. Sorry for that.